In this video, we shall be discussing on zero order reaction as well as the first order reaction represented in the form of differential rate equation as well as integrated rate equation for both first order as well as zero order reaction. Okay, now before we move on to the zero order reaction, suppose this is a reaction. Okay, then according to law of mass action, we write rate is equal to K A then B raised to the power small b. Okay, then for dx we can put dx by dt is equal to K A and B. Okay, so here see this one dx by dt, this is for the rate of change of either of the species, either of the reactant or the product. Okay, and this is the differential form of rate law. We can also say differential rate equation. Okay, now moving on to the zero order reaction. Zero order reaction. Okay, so suppose reactant undergoes reaction to give the product. Now rate is given by K naught. Let us take the rate constant as K naught. Okay, and then the concentration of the reactant. So since it is zero order reaction, it will be 0. Therefore rate is equal to K naught. Okay, then according to the rate law, we know rate can be represented as d by dt is equal to K naught. Okay, so this one you give it equation 1. Now this equation 1 is known as the differential rate equation. Okay, this is a differential form of rate law. Then in the next step, see, we are representing the rate law equation in the form of reactant. Okay, then you cross multiply, it will be d of r minus d of r equals to K naught dt. Integrating on both sides. Okay, integrating on both sides. On both sides we will get like this, minus d of r is equal to K naught of dt. Okay, now this minus sign will come out of the integration, and here K naught is constant, so constant will be outside. Okay, now we shall differentiate both the left and right. Okay, so here this will give r, this one will give K naught and t plus c. We can also write it I. Okay, so this c or I is called the integration constant or the integral constant. Okay, then the next step from here, okay, see, at t is equal to 0, okay, at initial state, okay, before the reaction or when the time is 0, that time the concentration of reactant is equal to the initial concentration, isn't it? Whatever the concentration of reactant will be left, okay, is equal to the initial concentration at time t equals to 0. Okay, therefore from this one, I think it is equation number 2. Okay, so from equation number 2 we will get, okay, from equation 2, so see, minus this r will become r naught is equal to K naught into time is 0 plus c. So we will know the value of c. Okay, therefore the value of c is 0, so it will be c only. Okay, so the value of c is minus r naught. Now this value of c we will substitute in equation number 2. Okay, so substituting value, okay, substituting the value of C in equation number 2. Then what do we get? We will get C minus R equals to K naught T plus C. What is the value of C? C we got as minus R naught, isn't it? Then next step will be, this one is K naught T, this one plus into minus, minus R naught. Now this minus R naught, you transfer this side, it will become plus R naught. Okay, so it will become R naught, then minus this R equals to K naught T, isn't it? Or we can also write K naught is equal to T, we can transfer to the other side and it will become like this. Okay, so we can either choose this one or this one. Okay, give any one of them, say suppose this one, okay, or one of them, just choose any one of them. This will be equation number 3. Okay, so equation number 3 or this equation, okay, both of them are same only. So equation number 3 is called the integrated rate equation, okay, or the integrated form of rate law. Now suppose, okay, suppose let's make it this one equation number 4. Okay, suppose see, this is the reactant, it gives product when time is 0. Okay, I mean before the reaction, let us take the concentration of reactant be A, the amount of product forming is 0, isn't it? When I mean at initial point before the starting of the reaction. Then after some time T, suppose the product is forming X, then the amount of reactant left will be A minus X. The concentration of the initial concentration minus the amount of product formed, so A minus X. Okay, now see here, R naught is the initial concentration, A is also the initial concentration, so it is A. Okay, then this is the concentration of the reactant after some time T or after some reaction, so this A minus X is that one only. Okay, so it will be and this is A minus X. Okay, then from equation number 4, okay, so from equation 4, see what we get, K naught equals to R naught, we write A, okay, then minus R, we write A minus X divided by T, so which is equal to, see, A minus into minus plus X divided by T. Therefore what do we get? K naught is equal to A minus X is 0, so it will be X by T. Okay, so this is equation number 5. We can also represent in this form. Okay, I mean for the integrated rate equation, okay, for 0 order reaction, so we can represent in this form. Okay, and one more thing, okay, I think I forgot to mention this one. This K naught is the rate constant for 0 order reaction. Okay, this one you have to remember. Now moving on to the next one, to draw the graph. Okay, I want you to go through the equation of a straight line, okay, which is y equals to mx plus c. So see, I think from equation 3 you can see R naught minus R equals to K naught T. Let's rearrange this one. Okay, so R naught minus this K naught T, bring this side, and this one you take it to the right hand side, or you can just exchange. Okay, so R equals to R naught minus K naught T. Okay, now this is of the form, you see, we are going to we are going to represent the graph as concentration and time graph. Okay, now comparing to as an equation of straight line, we have my equals to mx plus c. Okay, so listen carefully. Okay, here you see this c is called the intercept. If c is 1, then suppose this is 1, 2, 3 and so on. Okay, if c is 1, then that particular straight line, it may be like this or like this. It will pass through the point number 1 of the y-axis. If c is 2, then it will pass through 2, or it may be like this also. Okay, so it depends. It may be straight also. Okay, so if it is 3, then it will pass through 3. Okay, so like that. Then this m is called the slope. This is the x-axis, this is the y-axis. So same way here, you see this is y. Okay, this is the intercept, and this one is mx, x-axis, time is x-axis, isn't it? So see, suppose at this point is r naught. Okay, concentration is r. Now this point, okay, let me write this side. Okay, r naught. Now since this is of the form of equation of a straight line, so therefore it will have a straight line graph. Okay, and see, if the intercept is negative, then it will come down. If the intercept is plus, if the slope, if the slope is minus, then it will be downward direction. If the slope is plus, then it will be upside. Okay, so since here it is minus, therefore the direction will go down. Okay, now this is how the graph will look like for the zero order reaction. This is for the concentration versus time. Okay, this is how the graph will be. I want you to go through, okay, more detailed understanding with regard to equation of a straight line. Clear? Now with this same method, okay, with this same method, the process will be the same, but this time let us see. Okay, so for first order reaction, I'll do it a little faster this time. Okay, so first order reaction. Now there are not much differences, only in the integration part there will be slight changes. Okay, but the steps were same as that of the zero order reaction. Okay, suppose the reaction R gives the product P. Okay, the reactant gives the product P, then we know that the rate is given by, this time it is first order, so let's put K1 and R, and power is 1, so we don't have to mention. Okay, therefore this rate is minus d of R by dt is equal to K1 R. Okay, now this you give equation 1. This equation 1 is called the differential rate equation. Okay, now next one we shall go for the integrated rate equation. So for that we have to integrate, but before integrating, let us cross multiply. So here the concentration term, you bring it this side. Okay, and this dt you take it that side, so it will be K1 dt. Okay, now you integrate. So integrating, it will be like this. Okay, this, then this is K1, then dt. Okay, integrating on both sides, you have to mention here. Okay, then here minus sign will be out, and this will be like this. Then here K1 is constant, so it will be outside, so like this. Okay, then here this will give the value of L and R. Okay, the integration of 1 by R is equal to log R. Okay, so like this. Then here K1 D plus C. Okay, then we have to find out the value of C. So therefore let us put one condition. Okay, when T is equal to 0, okay, or at T equals 0, what happens? The concentration of the reactant will be the initial concentration, that is taken as R naught. Okay, so from equation number, this one make it 2, from Okay, equation 2, what we get? We shall get minus ln, that r will become r naught, okay, is equal to k1 into t is 0, okay, plus c. So c we will get minus ln r naught equals to, this one is 0, so only c, so c is getting this one. Now we shall substitute the value of c in equation number 2, okay, or we put, so substituting the value of c in equation number, what is it, 2, okay, so we shall get here c minus ln r equals to k1t plus c value is this one, we got minus ln r naught, okay, this is what we got. Then next step will be minus ln r is equal to k1 t minus plus minus minus ln r naught. Now this minus ln r naught, you bring it this side, so it will become plus, so it will be ln r naught minus ln r is equal to k1 t, okay. Now the next one is, you see, we know that ln equals to 2 point ln of any function, okay, ln x I suppose is equal to 2.303 log of x, so we shall change this ln in the form of log, okay. Then what do we get? This will be 2.303 log r naught minus this one also 2.303 log r is equal to k1 t. Now 2.303, 2.303 we can take common, isn't it? So 2.303 taking common, here this one is left, r naught minus here also this one will be left, so it will be log of r is equal to k1 t, okay. Then next step, you transfer this 2.303 to that side, okay. So grab this one, it will be log of r naught minus log of r is equal to k1t by 2.303, okay, 2.303, okay. You give this one as equation number, I think it will be equation number 3, isn't it? Then another one, see, we know that log of m minus log of n is equal to log of m by n, isn't it? So that same method we will apply here also, okay. So it will be log of r naught divided by r is equal to k1t by 2.303, okay. Now the next one is suppose, okay, suppose, so this is equation number 4, so equation number 3 and equation number 4 are the integrated rate equation, or they are called the integrated form of the rate law. Then suppose r gives p, okay, then initially the concentration of r is a and product form is 0, okay, when t is equal to 0, then after some time t, the product form is x, so amount of reactant left is a minus x, isn't it, a minus x, because x amount of product is formed, so the remaining amount of reactant will be a minus x, okay. Then here see, r naught is the initial concentration, so here initial concentration is a and r is the amount of concentration left, so here that is a minus x, okay. So from equation number 4 we get log of a by a minus x is equal to k1 t divided by 2.303, okay. This is how we can also represent equation number 5, okay. Now, okay, so that's all about the integrated form, okay, for both the zero order and the first order reactions. Now I want you to try out, okay, to find out the second order reaction. Okay, you find out the integrated form for the second order reaction. Okay, but before I end up the video, I'll give you a graph representation for this particular thing. Okay, I'll give you another task. I'll give you another task. Okay, so let us do log of, okay, this is a plot of log r0 by r versus time. Okay, now here you see y equals to mx plus c. If we compare with this one, this time in this case, see, there are two terms only, two terms. Okay, so here also, here there are three terms, which means here one term is missing, and that term that is missing is called the intercept. So from here, here the intercept is missing. Okay, if we do the graph based on this one, okay, if we take y-axis as a whole, this one, okay, instead of this one, so we have this one y-axis and x-axis is t. Then see, suppose this one is gone for now, okay, it is 0. Then see, y is this one, x is this one, then m is yours is this one, okay, k1. Okay, so this time the intercept is 0, so that means it is starting from 0 and the value is plus, so it will increase. Okay, it will direct upward, and here the slope is k1 by 2.303. this is called the slope. Okay, so this is how the graph will be. Now I have another task for you. Okay, I want you to draw the graph for equation number 3. Okay, from equation number 3 I want you to draw the graph for log of, okay, r versus time. Here I did for log of r0 by r in the time, and you do it for this one. Okay, and in the zero order reaction, I think I missed out something. I forgot to put the slope. Again, I forgot to mention the slope, so it was like this. Okay, it was concentration, that is for r, and this is time, and here at this point there was r0. Okay, so it was going down like this. And here the slope. Okay, so the slope was I think minus k naught. Okay, so this is the slope. Clear? Now I want you to do find out the integrated form for the second order reaction, and also plot the graph for log r versus time for first order reaction. Okay, and yeah, one more thing, you have to find out the graph representation for even the second order reaction. Okay.